Welcome to the deep dive. We've got some interesting source material today.
Mm-hmm.
It really looks at how core math concepts, maybe ones you're grappling with, actually show up in, well, pretty unexpected real-world spots.
Yeah, it's fascinating stuff.
And our deep dive today using this source is going to focus on how things like differentiation and integration appear in fields like livestock health monitoring and even food science.
Right. And the goal really is to pull out the key ideas quickly from this material. We want to show you how these, fundamental math tools are actually vital problem solvers, way beyond just textbook examples.
Okay, let's jump right in. And the source starts off talking about differentiation.
Yep.
Usually we think of the derivative as, well, measuring a rate of change, right?
Yep.
How fast something's changing.
Exactly. Speed, acceleration, that kind of thing.
But the source points to this kind of surprising application. Monitoring temperature changes, specifically inside livestock barns.
And what's really insightful here, the source argues, is why the rate of change itself, the derivative, is often more critical than the actual temperature at any given moment.
Okay, how so?
Well, think about it. A barn's temperature might be, technically within an okay range. Let's say it's acceptable.
Right.
But if that temperature suddenly jumps up or maybe plummets down really quickly, that rapid change, that can signal something serious, like equipment failure, maybe ventilation problem, or even just environmental stress that starts affecting the animal's health immediately. Differentiation lets systems catch those sharp shifts.
Before the absolute temperature maybe even hits a critical high or low.
Precisely. It flags the dynamic of the situation.
So it's less about an alarm saying, hey, it's 85 degrees, and more like, warning, temperature shot up 15 degrees in the last 10 minutes.
Exactly that. That rapid rate of change, that's the key signal the derivative helps capture. It's all about detecting a dynamic problem early on.
Using that instantaneous rate of change concept to monitor something vital for animal welfare. It's basically building a smarter, more responsive monitoring system using calculus.
That's a great way to put it.
Yeah. Okay, so that's differentiation, catching important changes in farming. Then the source kind of pivots, moves over to integration.
Shifts gears a bit.
And this takes us into food science, specifically food packaging design.
Yeah, and it's a nice contrast, actually. Differentiation is about rates, how fast things change. Integration, though, is fundamentally about accumulation, right? Finding a total amount, or in this case, volume.
Makes sense.
The big challenge in packaging design is figuring out exactly how much product a container can hold, especially when containers aren't, simple shapes.
Yeah, because let's be honest, not everything comes in a perfect box or a simple can.
Yeah.
You've got weirdly shaped bottles, curved plastic tubs, even like bags that squish around their contents.
Right. And trying to figure out the volume of those complex non-standard shapes using just basic geometry formulas, it's often, well, basically impossible.
You just can't do it accurately.
Exactly. And that is where integration becomes really essential. It works by sort of conceptually slicing that complex shape into countless infinitesimally thin cross-sections.
Like super thin slices.
Super thin slices, and then it sums up the volumes of all those tiny slices. That's the core idea of integration, right? Summing things up.
Okay.
And doing that lets designers and engineers calculate the total volume inside that weird shape with really high accuracy, which is crucial.
Crucial for what specifically?
Well, for manufacturing consistency, for one, making sure every bottle gets filled correctly, and also for legal stuff like labeling requirements, you need to state the volume accurately.
And making sure, the customer actually gets the 32 ounces of juice the bottle says it holds.
Exactly. It ensures fairness and accuracy all around.
So, okay, we've got the derivative being used to spot potentially dangerous, rapid changes in a barn's environment. And then the integral being used to make sure your, fancy curved bottle of olive oil actually holds the amount stated on the label.
It's the same fundamental calculus toolkit, just applied to solve really different but, equally practical real-world problems.
It definitely shows how these math tools give us a flexible way to understand and quantify things around us, whether it's tracking changes over time or measuring capacity.
Totally. It's about modeling the world mathematically.
So let's wrap this up. What's the main takeaway here for you listening as you maybe study differentiation and integration?
Well, based on what we've seen in this source material, think about these examples, using derivatives to catch those vital, fast shifts in agricultural settings. using integrals to guarantee the volume is right in everyday things like food packaging.
These concepts, they aren't just abstract math problems on a page.
Not at all. They're genuinely powerful tools being applied right now to solve concrete challenges. Improving animal health, making manufacturing more efficient, ensuring you get what you pay for.
It really makes you think, doesn't it? If calculus helps manage barn temperatures and design juice bottles, what else is out there?
That's the question, right?
Where else are these fundamental mathematical ideas working behind the scenes, enabling innovation and solving problems in ways we might not even notice day to day? Worth keeping an eye out for.